Okay, so switching gears, we're going to focus on a Byzantine adversary, a consensus protocol that works for n parties, where the adversary controls less than a third. This is the optimal number of parties you can handle in an information theoretic setting, as we've shown in lower bounds yesterday. And what you're seeing on the board is the protocol that we've developed yesterday. So we spent 2 hours on reaching to this point. I will try to give a quick summary of this protocol. So remember, this is a protocol that works in views. So in every view there is a primary and everybody else is a backup. And basically, you can see here there is 5 rounds of sending messages. So in a synchronous model, what we would do is after 5 rounds, we would change the view. So we would move from view 1 to view 2, right? So every 5 rounds, we would change the view. And so we all know which view we are in. If we're talking about the partial synchrony model, we'd have to use a more complex protocol to decide when to change views. What you see on the right side is the protocol. When a new primary arrives, it has to choose which value it wants to send to everyone. Remember, it can't just send its own input, because it could be that there was a decision in the previous view or in some even older view, and so this new primary must make sure that it's choosing safe decisions. So this is this view change. And so in the view change, every replica reports to the primary what is the value and what is the view number that it believes is the highest one that it received a lock. And so if it received a lock, there is some potential that somebody else decided. And so we're using the lock as a precursor for decision. And basically what the primary does is it waits for n minus f of these locks, and it chooses the one with the highest view number. And the risk here in the Byzantine setting is that some replica gives a lock and a lock value that didn't really exist, in the sense that this lock is some message that an old primary sent, but maybe no primary really sent this. So the way the primary verifies that what the replica sent is indeed something that happened is when it receives a lock for some value v prime in some value prime in some view v prime, it also checks that it received n minus f echo 2s, this is a typo here, for v prime and value prime. Okay, so by checking that there's n minus f echo 2s for value prime and v prime, this implies that the reliable broadcasts of the primary succeeded. And if you remember, yesterday we talked about this reliable broadcast property, which basically is written here. So you see that the primary sends a message, and then the replicas echo this message. And if you have n minus f echo 1s, you send echo 2. And if you have n minus f echo 2s, this is when you accept the message and create a lock. And so the properties of reliable broadcast is that if I accept a lock, I've seen n minus f echo 2s. And what I'm guaranteed is that everybody else will see f plus 1 echo 2s. Because if I see n minus f echo 2s, then for sure everybody else will see n minus 2f, which is at least f plus 1. And so all the non-faulty will send an echo 2. And if all the non-faulty will send an echo 2, then 1 round later, all the non-faulty will receive n minus f echo 2. And so this condition will hold. They will receive n minus f echo 2s. And so this means that if I see n minus f echo 2s, all non-faulty will see n minus f echo 2s. And moreover, we've shown that there's a non-equivocation property. There's only one value that the primary can send that receives n minus f echo 1s. Okay? So this basically means that if, again, we're back to the primary, if it receives a lock from a replica, and it also receives the appropriate n minus f echo 2s, it is essentially a signature that this event happened, right? It's an information theoretic way of guaranteeing that this event happened. And then what we said is that the risk we still have is that a malicious primary, so now a malicious primary can't just invent old values, but what it can do with the malicious primary is send values that are not the maximum ones. Remember that for safety, we need the primary to choose the maximum of all the locks and lock values that are received from the replicas. And so the way we handle this is basically by whenever a primary sends us a message, so in view v, it sends us some value, and it tells us that it took this value from some older view u. So v is the current view, and u is the older view that the primary is claiming this value came from. And what the replica does, it tests, first of all, it tests that this is indeed the case, that n minus f echo 2s for value and u did arrive. This means this value and u are indeed a signature of the old replica. But this blue test is also very important. It basically tests that the value that the replica is using is larger than the highest lock that I've seen as a replica. So if as a replica I've seen a certain lock, I do not accept messages or values that are older than that. I will only accept things that are at my lock or larger. And this is going to be important for the safety argument. And so these are the two additional conditions that we're adding to the reliable broadcast protocol. And the reliable broadcast protocol essentially ends here, where you receive n minus f echo 2s. And at this state, you send your lock, set your lock, and you send a lock message. And just like a regular Paxos protocol, if you receive n minus f locks, then you decide a value. Okay, so this is kind of a overview of all this protocol. Any questions about this protocol? It's a little bit complex, and we talked about it yesterday, and I want to make sure that I'm not jumping too quickly forward with it. So if you have questions, better ask them now. Okay. So one person asked me, who was this person that asked me about validity yesterday? Yeah. So said, well, you know, you've shown us that this protocol is safe and live. We went over the sketch, and I'm going to go over this proof a little bit in more detail today. But what about validity? So remember, in validity, we want to say that if all non-faulty start with the same input, then this is the decision value. This must be the decision value. So in particular, at least in the protocol, the way I've wrote it here, yeah, so this is the property. If the input, if they all have x, then this x must be the decision value. And if the first primary is non-faulty, then we're fine, because this non-faulty uses this value. But what if the first primaries are faulty? Okay, so they can choose whatever value they want. And so, you know, this is something that I didn't consider yesterday. So, so here's kind of the way to approach this. It's basically to say that we will not choose a first primary as one of the parties. We will basically assume there was some virtual primary. And what did this primary do in the first round? So in the first round, the primary just sends a message to everybody. So what we will assume is that this thing happened by the virtual primary, and our inputs are what the virtual primary sent to us. Okay? So if all the non-faulty have the same value, it is exactly as if the virtual primary sends this value to everybody. So in a sense, the first round of this protocol will start not by the primary sending, but basically by everybody starting from round 2. Okay? And then, if indeed there is the same value, then everybody will decide at the end of this round. So this is for validity. And now we'll go over the safety argument. So the safety argument, again, I'll repeat it. It's an induction argument that just looks at the first view that any non-faulty decides. So let's assume this is view V star, and the value is x. And what we would like to say is that anytime we accept a send, so we receive n minus f echo 2s from a party in a view that is larger than V star, then this must be of the same value x. So if this is the case, it means that, well, if there is a value that reaches the fact that it's being accepted, then it must be the same value as the decision value that happened in V star. So this is why we will always be safe. And the reason this is true when we are in V star is because of non-equivocation. So due to non-equivocation, we basically will not have n minus f echo 1s for one value and n minus f echo 1s for the other value, right? We've seen that yesterday. And so this is the base case. And for the induction, we actually want to state a stronger statement. This is very standard in induction, where you state something stronger in order to receive your claim. So we'd like to get these three properties. So the first one is that indeed, if a primary sends a value that's actually accepted, so there is at least n minus f echo 1s, then it must be with the same value. The second property that we'll maintain by induction is that there is a group of f plus 1 non-faulty that are locked on the value x with a view that's at least V star. So these will be our guardians. There's a group of non-faulty parties that will make sure that the decision will be maintained through views. So even though there may be one party that decided, there's a large amount of non-faulty that have this property. And in addition, we can talk about, in addition to having at least this core of f plus 1, we have an additional property for every other non-faulty, which is that if it is locked on a view that is larger or at least V star, then it has the same value x. And if it's, or otherwise, it's locked on a lower view. So these are kind of the two cases. So this is the proof. It's again pretty simple. So let's look at the first round, the base case at round V star. So in view V star, what we are guaranteed is that if somebody decided in V star, it means that there were n minus f that sent a lock to the decider. Remember that the way you decide is by receiving n minus f locks. But if somebody received n minus f, it means that n minus 2f out of them are non-faulty. N minus 2f is at least f plus 1, and so f plus 1 is the core. This is the core of f plus 1. And since we are now in view V star, this core of f plus 1 non-faulty are locked on V star. Obviously, V star is the highest view because, well, this is the current view. So this is why these three induction claims hold for the view V star. Is that clear? Yeah, and then we'll do the same thing by induction. So we will assume that this is true for all views that are V star and larger, V, and we will prove this same 3-point claim for the view V plus 1. And basically, it depends on what value the primary uses. So if the primary uses a view that is at least V star, then what do we know? We know by induction that the only accepted value must be with value x. Okay, so if the primary decides to use some value that it happens after V star or at V star, then it has to be x. And so indeed, this primary might cause decision, it might cause locking, but if it does cause locking, this core will still be locked on the value x, but maybe the lock will be, instead of V star, it would be on view V plus 1. So we might increase our locks, but we keep the same value. And similarly, this property here, 3, either a non-faulty doesn't see this value, or it gets locked but it gets locked on a value x. So again, the induction, these three statements of induction hold. And the last case is if a primary uses a view that is lower than V star. So it's a malicious primary, or maybe a confused primary, that's not taking the maximal view that it hears about. So in order to make progress, this primary needs to receive f+1 echo 1s. Right? This is kind of the core of the protocol, or the main thing that we block in the protocol is we have this core of f+1 non-faulty, where by induction they are locked on view at least V star. So if you try to send a view that's lower than V star, they will not send an echo 1. So if f+1 people block, then you will not receive an n-f majority, right? Because there's at most 2f. So just a quick reminder here. Yeah, in the protocol, this is this blue phase. This is where you check that the value is at least as large as your lock. So these f+1 guardians have a lock that's at least V star. And if a malicious primary tries to provide an old view, then they will block it from making progress. Okay, so this is the safety argument. Any questions about this safety induction argument? Great, so now we go back to liveness, and what we'd like to show is that if we have a non-faulty primary, or we could say, also in the case that all primaries have this, all replicas have the same value, then in that, in those 5 rounds, everybody will reach a decision. So again, we will do this in the case that there's a non-faulty primary and the system is synchronous. And the important thing here is that during the view change, the primary hears from all the non-faulty. And because it hears from all the non-faulty, it will choose the maximum one. And because it chooses the maximum one, then these two things will happen. First, the value that the primary chose is one that has n-f echo 2s, and therefore everybody else will also see this. This is the reliable broadcast property. And also, since you've chosen the maximum, then this will be at least as large as whatever your lock value is. And so they will all send this echo 1, and after all the non-faulty send echo 1, everything else in this protocol is unconditional, meaning that you will send echo 2, and after sending echo 2 you will send lock, and after sending lock you will all decide. Okay. And then what we talked about is this adding this additional twist, which we'd actually like to maintain liveness even if the system is not synchronous. And so the problem here is that in the asynchronous system, you cannot wait for all non-faulty to give you a response in view change. All you can do is wait for n-f responses. And it could be that in these n-f responses, you actually receive f malicious responses, and so there are f non-faulty that you did not hear from. And so the risk here is that there might be some non-faulty that is locked on a high view, and you, when you're doing a view change as a new primary, do not see this fact. And since you do not see this fact, you choose a value that's smaller than this maximum. Now, you can wait for n-f responses during view change, and that n-f might not be of all non-faulty. You might hear just f+1 non-faulty, f faulty, and there might be, in the asynchronous model, f non-faulty that are slow. And so that is the risk here. And so the risk here is that there is a hidden lock. There is some honest replica that has a lock, and while we're doing view change, we cannot, we missed it, and since this replica will not respond to lower requests. It will block the echo 1 message, and therefore we will lose liveness. This new primary will not be able to make progress because you will not have n minus f parties that will send echo 1. In particular, this party that has a higher lock that you ignore during view change will not accept your message. So as I said yesterday, we can only just add one more round. And the idea, again, is that instead of when you reliable broadcast arrives, instead of locking at this point, we will say that at this point we have a key, and then we will send n minus f messages. And once you get n minus f keys, that will be a lock. Okay, and what is the property here? The property here is that now if a non-faulty has a lock, then there are at least f plus 1 that have a key. So previously, it could have been that there's just one non-faulty that has a lock, and we miss this non-faulty because we're reading from n minus f, and we miss this one non-faulty. But now we're kind of lifting up this information. So if one honest has a lock, there's at least f plus 1 that have a key. F plus 1 non-faulty that have a key. So these f plus 1 non-faulty that have a key, they have to intersect the n minus f that I read. So there's at least one honest that has a key. And so this is why we're going to be safe. And so what you can see here is, again, this protocol that we just added one more round that after you receive n minus f echo 2s, you send a key, you set your key, and then you send the key. And after n minus f keys, this is when you set your lock. And then when you're doing a view change, you're sending your keys. And when you check whether you want to send echo 1 or not, you compare u is a key, to the lock you have. Okay, so this is kind of this additional twist, and this gives you this stronger liveness property. I will go over this because I want to focus on randomness. So, okay, good. So now what we want to do is we want to elevate this to using randomness. So until now, I've spent 3.5 hours using no random bits, and now we will use some random bits. And so, you know, this idea of a revolving coordinator, the problem here is that a malicious attacker can basically corrupt the first f coordinators, and so the running time will be f plus 1. As you've seen, there's a lower bound. Any deterministic protocol has to run for f plus 1 rounds. And so what if we had this ability to randomly choose a leader in a way that nobody knows to predict in advance who the leader would be? So the naive thing, so here's kind of the functionality. You have to request, and at least f plus 1 honest need to request in order for this functionality to start. And the functionality gives you back an answer. Here's the leader. And let's assume that this is a very weak type of leader election functionality, that with constant probability, everybody sees exactly the same value, and this chosen party is not faulty. So note that with the remaining probability, anything can happen, right? So this is like a multi-party computation that with probability 1/2 gives you a honest party, but with the remaining probability, you can see complete disagreement, right? There can be a complete disagreement about who we're electing. So this is the functionality, and you might try to use this for a static adversary, and basically instead of having a revolving coordinator, just every view you would do a random leader election, and then choose the new primary based on this functionality. The problem here is if you have an adaptive adversary. So if you have an adaptive adversary, it will just wait and see who is the elected primary, and then attack this primary, right? So it's a very natural approach for adaptive adversaries. And so this is kind of the standard approach. You know, you wait till somebody is elected, and then you corrupt this elected official, right? You don't have to corrupt everybody. You wait till it's elected, and then you corrupt. And so what is the solution? So the solution is to basically let everybody be the primary, right? So instead of electing one person to be a primary, you all get to be prime ministers. And then after some time, we choose in hindsight who was the real one, and everybody else is a decoy. So this is a very simple trick to defend against adaptive adversaries. So the first round, basically everybody behaves like a primary. But in fact, this is just creating a noise. And then in the second round, we will choose who was the real primary and who was a decoy. And if I'm an adaptive adversary, I don't know in the first round who to corrupt, right? Because I only learn about the real primary in the second round. So I'm using the fact that even an adaptive adversary cannot know the future. And so why is this good? It's good because with the constant probability, there's a good primary that's being chosen. And even if a faulty primary is chosen, or if different people believe that different primaries are chosen, then we should be fine because we're already fine with any malicious behavior. So in particular, even if I think that one Benny is the primary and somebody else thinks that another Benny is the primary, this is still as if it's a malicious primary that has a split brain of two different Bennies. So yeah, this is kind of a high-level intuition of why safety is maintained. So here is the previous protocol that we've discussed. This is the same protocol, and what I want you to look at is just nothing is going to change except the first line. The first line is going to change. So this is the first line. Here we had one primary, and it sends a value. And now we're going to change this first line into two lines. That's it. Trust me, nothing else changed. So now everybody acts as a primary and sends a message. That's first round. And second round, we run this oblivious leader election to decide who to listen to. Okay, that's the only change. Everything else in this protocol, all the stuff that we've talked about remains. We still need this liveness and safety guarantees and so on. And so why will this work? Again, so for liveness with with liveness with constant probability, we are guaranteed that a faulty primary is elected. And in this case, this non-faulty primary will act just like we said. But in case where there is disagreement about who the primary is, or in case that the primary is faulty, well, then it will just send some malicious messages. But we are completely, yeah, it's okay. We are completely resilient to a malicious adversary that can send any message it wants, right? Information theoretically, no matter what the primary does. And so this is kind of how you modify this protocol to work at least in the synchronous model for an expected constant number of rounds, right? Because now you have kind of a geometric series where with constant probability we will be electing a good leader. If we elect a bad leader, what we know is that safety will be maintained. This is exactly what we've always worked on, right? That even a bad leader cannot make bad decisions. This is the safety property. But if you have if you are elected a good leader, then this good leader will give you liveness, will give you decision. So with constant probability, you will make a decision. So in the next slides, I will now go over how you implement this oblivious leader election. And if you had 3f plus 1 and you have multi-party computation, then you can easily implement leader election. This is kind of a simple, I guess, linear MPC. But the problem is that as you've seen, as you will see, multi-party computation requires verifiable secret sharing, and the verifiable secret sharing that was described requires broadcast. And so it's kind of this chicken and egg problem where we are trying to implement broadcast, so we better not use broadcast to implement the constant round, expected constant round broadcast protocol. So the solution will be to try to use a weaker notion of verifiable secret sharing that will be strong enough for this oblivious leader election. And this is going back to Micali and Feldman's paper, graded verifiable secret sharing. And I'm going to use a alternative formulation, which is called moderated verifiable secret sharing. This is the Katz and Koo approach, but it's essentially very similar. And so the way at least I see this is that we're going to use gradecast to tailor make this MPC. And in what sense is tailor-made? It's very, very far from perfect security. It's not even statistical security. It actually has a constant probability of error. So it's a strange type of MPC that with constant probability have no guarantee. But luckily enough, this is good enough for oblivious leader election, because it's okay that with constant probability there is complete confusion, because we spent a lot of time building a protocol where the primary can be completely malicious. So this constant error probability equates to a primary being completely malicious, but in a constant probability we actually have a good primary. Right, so the path here is that we build gradecast, and from gradecast we will build this moderated verifiable secret sharing, and from moderated verifiable secret sharing, oblivious leader election, and from oblivious leader election we will plug this into the protocol that we've seen to get a constant time expected Byzantine agreement protocol. Okay, so is the plan clear? Good. Okay, so what we'll first do is gradecast. And you've already seen this. You've essentially seen a stronger version of this, which is reliable broadcast. But I will kind of go over gradecast because it's a fundamental tool for synchronous protocols. And anytime you have a protocol, you can always just slap gradecast onto it. It typically helps. So there's a dealer that has a typo and an input M. And the goal here is to output a value. But the reason it's called gradecast is that we're also grading this value. So we're not only returning an output, but also a grade. And this grade will be either 0, which is bad, 1, which is medium, or 2, which is really great. Okay? And what are the properties? So the first property is that if the dealer is non-faulty, then everybody will output the message that the dealer wanted to send, and this value great, right? High grade. And the other property is kind of this type of agreement property, which basically says if some non-faulty accepts a message M prime with a grade of 2, then what I know is that all non-faulty will accept this same message M prime, maybe with a grade of 1 or 2. So I can't guarantee complete agreement with 2, but you will see either 1 or 2. Right, so this is the property that we want to obtain. How do we do it? So I will start in the first round. Any suggestions what could be the first round? There's not a lot of choices, right? The primary has to, the leader has to send the message to everybody. So what can we do in the second round? Any choices in the second round? Yeah, so the only thing you can do is echo this message, right? That's it. Okay, so so something non-trivial has to happen. So maybe it's in the third round. So what do we do in the third round? Yeah, we count, and if we see a certain threshold above n minus f, we will send this one more message, right? This echo 2 type message. And that's it. That's the end of the protocol. So it has 3 rounds, and at the end of these 3 rounds, we will evaluate our position, right? We will grade the sender. So if we receive n minus f echo 2s, then we give grade of 2. This is how we're grading this sender. If we don't see it, then if we just see f plus 1 echo 2s, we will give a grade of 1. And otherwise, we will give a grade of, we will just do a typo and give a default value. So this is the protocol. Any questions about it? Very, very simple.
In rounds 2 and 3, you send to everybody?
Yes. If you had cryptography, you could do other trick. Yeah, you send to everybody. It's all to all. Yes. Right, so here's the protocol on the left side, and on the right side we will basically do a proof. So first of all, we use this same idea that we've went through many times, that you can't have n minus f echo 1s for v and n minus f echo 1s for v prime. Right? The reason is that in the intersection of these is n minus 2f. N minus 2f is at least f plus 1, and so there's at least one honest party. This honest party will not send both v and v prime. And so this basically means that if two parties have a grade of 1, then it must be the same value. Right? Because whatever value is sent in echo 2 has to be the same for all parties. If the dealer is non-faulty, it's clear that everybody will receive n minus f echo 2s. Right? Because all the non-faulty will receive the dealer message, will send echo 1, and then all the non-faulty will receive n minus f echo 1s and send echo 2. All non-faulty will see n minus f echo 2. So again, this is an easy property. And the last property is that if somebody sees n minus f, somebody has grade 2, it means it sees n minus f echo 2s. And again, we're just using this fact that if somebody sees n minus f echo 2s, then there's at least, everybody else sees at least f plus 1 echo 2s. If they see f plus 1 echo 2s, it means they will be graded with grade 1. Okay? So you've already seen this. You should be able to build this yourself. So this is gradecast. And basically, every time you have a broadcast protocol, so by the way, what's different between these properties and the broadcast? Why is this weaker? In what sense is this weaker than broadcast? In what sense is gradecast weaker than broadcast? You're not? Right, so what is the additional property that broadcast has that gradecast doesn't have? So if I receive a grade of 2, I know everybody received the same thing. But if I receive grade of 1, I don't know everybody received. I know that if they received the same value, but I don't know that they received. So that's the difference here, right? The difference here is that a non-faulty can cause grade 1. In broadcast, I know that if I received M, everybody received M. In gradecast, if I receive grade 1, all I know is that if you received it, you received the same message, but maybe you did not receive anything. Right? So maybe you have grade 0. So that's the difference. So it's a weaker property. Okay, but still, the idea is going to be to replace the broadcast in VSS with gradecast. And so this is kind of an extension of this idea that Katz and Ku did, which basically said there are going to be two different designated parties. One is the dealer. This is the dealer of the VSS, right? So VSS has a secret. The dealer is the party that has a secret. And the moderator is some party that we just call moderator. It could be the dealer. It could not be the dealer. And we will explain why we use this moderator later on. But imagine there's some additional auditor that checks the protocol. And so what we're going to do is a generic reduction that takes a VSS that uses broadcast and replaces each one of these broadcasts by this following simple protocol. So suppose that in your VSS there is some stage where somebody sends a broadcast. If you remember 2 days ago, there were complaint messages or messages where you send your shares. You think that these two shares are not the same, so you broadcast them. So there are many cases where parties broadcast. And so if a broadcast of a message M by party J, what you do is basically, party J runs gradecast with this message M. And then the moderator waits to receive information from this gradecast. And let's say that it received the value M prime. And what the moderator does is it runs gradecast on M prime. So the sender J does its gradecast, and the moderator, think about it as like an auditor, it takes whatever it heard from J, from the result of this gradecast, and it gradecasts M prime itself. And the way we're going to consider the output of this is the following. So now for every broadcast, there are two different outcomes. There is the message that you received and the grade in the first gradecast, and the message that you received in the grade in the second gradecast from the moderator. And here's what we'll do. If the moderator's gradecast is not 2, then we would basically say there's a problem. Or if the moderated gradecast is 2, so you get a perfect grade, and the sender's gradecast is also perfect, but they're disagreeing on the message, then you also decide this is not okay. Okay, so this is the protocol. Basically, there are two cases where you become upset. One is if the moderator doesn't give you a grade of 2. The other is the moderator gives you a grade of 2, and the sender also sends with a grade of 2, but the messages are not the same. So somebody is cheating there. And here's kind of the property that we want to prove. We want to prove that if any non-faulty has set an OK bit, then the VSS properties hold. Okay, so remember here we have kind of a way to downgrade our OK to be a false. And what we want to say is that if there's anybody who has an OK, then things are fine. And so here is the reason. So if there's any non-faulty that has an OK, what does it mean? It means that we have to look at kind of the negation of these properties, right? So it means that, well, it must be that the moderator had a gradecast of 2. It means that this value is correct. And it means that if the sender also had a gradecast of 2, which means it was a correct sender, then it was the same message. So if I have an OK equals true for all broadcasts, it basically means that I have a gradecast of 2 from the moderator, which means that everybody else has at least a grade 1. So everybody see exactly the same messages that I've seen. And therefore, the broadcast properties hold. And in terms of correctness, if there was an honest party J that sent a message, then it will also have a gradecast of 2. And since there is equality here, because I did not send it to false, then any honest broadcasts will be the broadcast that the moderator sent. Right? So this is the reason, Ben, you have till 11:15? Okay. This is the reason why we essentially have this property that if one non-faulty has an OK, then we are fine in terms of the broadcast properties holding. And since the broadcast properties hold, then the VSS properties hold as well. This statement also says that if the moderator is non-faulty, then everything will work out. And so now that we have a way to create a moderated verifiable secret sharing, we're going to build an oblivious leader election. And again, this is kind of simple, really simple MPC. So what we'll do is just for every party J, we will have every party I build some random coin, and then just add all these random coins together to get a random ballot for this party. Okay, so this is kind of a standard type of MPC, a linear scheme where everybody does a VSS. So if I'm party J, then everybody does a VSS for me, and I will be the moderator for all these instances. And the trick here is that what we will do is we will look at these OK messages, and if there is any of the moderated VSSs that result in a problem, then I will basically give this moderator J a 0 score. So my goal is eventually to choose the party with the highest ballot. So basically, if I detect a malicious behavior, if I detect that the OK is false, then I will give this party the lowest score, and so this party will not be elected. Right? And so the way this analysis works is that with a very large probability, there's going to be no collisions between all these random coins. Since we're choosing them, say, in a scale of n to the 4, we have only n parties, so there's very little probability of collision. And so if we have no collision, then with constant probability, there is going to be some non-faulty that's going to have a higher ballot than all the faulty parties. And really the only risk here is that maybe this VSS will be failed. And so if you have an OK on this party, it means that you do not zero it out. It basically means, remember that the previous scheme says that if you have an OK, it means that the VSS properties hold. So if you decide to not zero out this party because your OK is true, it basically means that the VSS properties hold. This means that all this secrecy properties of VSS and the randomness hold, which basically means that this MPC that's computing the ballot is correct. Okay, so what we've seen here is the full construction of how we start with gradecast. We use this to take a VSS protocol and with gradecast, and this moderated gradecast, and then we build from this moderated gradecast an oblivious leader election, and then we plug in this oblivious leader election into the consensus protocol that we've been working on in the last 3 hours. And this protocol has the ability to withstand malicious primaries, but in constant probability there's going to be a good primary, and then we're going to get progress. So any questions about these constructions? Yeah, so in the 10 minutes remaining, I'm going to say a few words about why we need a quadratic number of messages. I remember that in the first day somebody asked, so for verifiable secret sharing, do we need a quadratic number of messages and not n log n? And if you notice, the protocol that I've presented, this primary backup protocol, if you go over it, you actually realize it requires every round requires a quadratic number of messages. So if you have a constant expected number of rounds, then you have a the expected number of messages is quadratic. The problem here, the open problem here, is to do the oblivious leader election in a quadratic number of messages. I don't know how to do that, because currently we're doing n squared verifiable secret sharings. Each verifiable secret sharing needs a quadratic number of messages. So at least this solution was n to the 4. I think you get down to n to the 3. I don't think you can get down to n squared so easily. Yeah, in the random oracle model, you can get n squared oblivious leader election. I don't even know how it can be done without the random oracle model. But the reduction itself requires just n squared messages. And so this question of can you solve a Byzantine agreement with less than n squared messages really depends on what are the adversary assumptions that you make. And it really depends on whether you have a static adversary or an adaptive one. So if you have a static adversary, then you can actually solve Byzantine agreement quite easily by using randomization. So this is kind of the US jury system. Instead of all of us making a decision, we will just choose a random subset and let this random subset make a decision. It's a very efficient way. And if we have only, let's say, 1/3 malicious in the whole population, then when you do a random subset, you will probably get quite close to that. Yeah, so this is kind of the high-level approach. Is you choose a random polylog size committee. Since the adversary is static, it controls only a small fraction of this committee, and you would run a Byzantine agreement on this committee, and this committee would report back. So at least for a static adversary, it's quite simple. So what I'm going to show is a lower bound when the protocol is deterministic. So you can think about deterministic protocols as an initial reason why quadratic messages are needed. Again, in a deterministic protocol, there is no problem of being adaptive or not adaptive. So this is this lower bound from 82, Dolev and Reischuk, which basically shows that you cannot do more than, you cannot have a protocol that sends less than a quadratic number of messages. In particular, if the number of failures is f, then you have to send at least f over 2 squared. So for this protocol, this lower bound, you will give me a protocol, and I will be the adversary, and I will build an attack on this protocol. And so the first thing I will do is see what happens if a party receives no messages. So you give me an algorithm, and I will see what happens if it receives no messages. And let's assume without loss of generality that it never decides 1. So maybe it decides 0, or it doesn't decide at all. But it has to do something, so let's assume it never decides 1. And so the proof approach is going to be the following. We're going to create 2 different worlds and reach a contradiction. In the first world, everybody is going to decide 1. And we're going to have a set of f over 2 that are corrupt, and we'll call this set C. And in the second world, we're going to corrupt f over 2 additional parties. And what we're going to do is one of those parties that we corrupted here in C, we're going to actually change them back to become honest. Okay, so we're going to add f over 2 more corruptions, but take one party that we previously corrupted and make it honest. And so the properties that we'll have here is that all the honest in world 2 will see the same thing, the same view in world 1 and world 2. So everybody that's honest except P will not be able to differentiate between world 1 and world 2. So obviously the parties in world 2 will have to decide 1, because in world 1 you decide 1, so in world 2 you also decide 1. But poor party 2, we will make sure that party 2 receives no messages. And since it receives no messages, we said it cannot decide 1. And since it cannot decide 1, we'll reach a contradiction. So that's the proof approach. It's pretty simple. So yeah, here's the 2 worlds. In world 1, we just have f over 2 corrupt. In world 2, one of those we will kind of change from corrupt to be honest. And yeah, in world 1, everybody decides 1. And in world 2, we're going to add additional corruptions. And this node P in world 2 receives no messages. And these worlds are indistinguishable. So here's the kind of attack. So you choose a set of f over 2 parties. And here's how you corrupt them. So this is the set of f over 2 parties. And basically, they run the same protocol. So they run as if they're honest. And you do 2 different modifications. These modifications work even for omission failures. So each member of C, we're not going to allow them to send messages between themselves. So here are 2 members of C, and if a message is sent, we're going to block it. So this is kind of one behavior that we're going to do. This is an omission type behavior. And the next thing we're going to do is we're going to block, for every member in C, we're going to block the first f over 2 messages it receives outside. So we'll just look at the first f over 2 messages that arrive to a party inside C from parties outside of C, and we will block those messages. So here are these 3 parties. These are the parties that are sending messages to this node here in the middle. And if these are the first f plus 1, then we will block them. The remaining messages we will accept. And so this is what we'll do. Let's assume that we start with initial input of 1, and every honest party decides 1. And now we're going to use the fact that we're sending few messages and basically use, again, averaging argument that says that if there are so few messages, then there has to be some party P that receives at most f over 2 messages. right? So if everybody in C receives more than f over 2 messages, that means that we've sent more than f over 2 squared messages. So this is just a counting argument. So let's focus on this poor node P inside the group C that we corrupted in world 1 that received less than f over 2 messages. And now what we're going to do is flip the switch on who we corrupt, because all we've done is omission failures. In an omission failure, we can either decide to corrupt the sender or the receiver. So we'll just flip this switch. And so here's X. X is the group of parties that are sending P a message. Since P received at most f over 2 messages, then this set X is also small. It's only f over 2. And so we take this group X and we corrupt them. We are still allowed to corrupt f over 2 because we only corrupted f over 2 in the first round. And how do we corrupt? Well, we simply block the first f over 2 messages that X sends to P. Right? And this is a small group, so we're okay. Yeah, it's easy to see that any other honest party, so except P, sees no difference in terms of messages, right? So exactly the same view is seen in world 1 and world 2. In world 1, everybody decided 1. In world 2, everybody still has to decide 1. But poor party P here is honest and receives no messages, right? It receives no messages inside C because we said that we blocked all messages inside C. It receives no messages outside of C because the protocol sends at most f over 2 messages. And this group of X that send these messages, we block them. So this is basically this Dolev-Raychuk proof. And if you massage it a little bit, you can extend it to randomized protocols, but again, against stronger adaptive adversaries. Yeah. So this concludes this session on consensus. Thank you.